Hello and welcome to this class on how to use the software Labspec. The software Labspec is made by Horiba, which is a Japanese company. It's made to be used with the Raman equipment, but it's a software that is extremely flexible. We are using, in this case, Labspec version 5. I think there's some modern version of Labspec, but this works way better than the new ones for some reason, even if it's like 20 or even more years old. It's one of the best softwares for data fitting when it comes to spectra like Raman spectra, but also FTIR, XPS, XRD, anything that looks like a spectra can be fitted very well using this software. But I will go and explain step by step what you can do and how you can achieve your goal using this software. I think it's available for free, but it's relatively easy to find around. Just I will use this spectra that I acquired. This is a curcumin spectra. Curcumin is a molecule in the family of carotenoids that is can be found in spices like turmeric powder, and it has a really nice Raman spectra that I will show you now. Now, if I just take this txt file that contains the information about the operator name, all the parameters, etc. If I drag this, the software cannot open the data because it cannot understand exactly what I'm trying to do. Doesn't recognize the format of the file. So what we can do is open our txt file, remove all the unnecessary information like this, and save it with a name like before. I use curcumin only. It needs to be in this format: one column for the x and one column for the y with a separator in the middle. And if we do like this, then we drag our file, and now we can open it correctly. As you can see, this is not the best data, but I choose it on purpose because I wanted to show you how to work with it. And you can see here the intensity of the spectra, and on the bottom, let me just improve a little bit this. We can do it like this, I think. Yes. In the bottom, you can say the positions in centimeters minus one. So, what can we do with this kind of information? Well, with this kind of software, well, we can do basically everything, starting from baseline removal and noise reduction. In this case, the noise doesn't look so bad. You see, there's a bit of noise going on the curve. There's some other issues with the noise, like this waving shape that is unnatural. What we do have a problem with is this strong background curve here. So first of all, the best thing to do is to choose the region we want to work with and to try to reduce this background. So there are a lot of functions that we can use in order to do so. We have the baseline removal tool here, and we can try to automatically find the best solution, and it gives us this very bad baseline removal. Well, I use the function lines. If we ask him to remove a polynomial, we can choose the degree of the polynomial or something like this. It doesn't really work well, right? What with the third degree? It works a little bit better, but still, this is garbage. It's not what we want to do. And we can also tell him not to be exactly on the curve, but the result, it doesn't change much. So we can remove by lines, by a split line, or we can remove using a polynomial, the baseline. I often use the line function because it gives me a little bit more control on what's happening. And we can do it manually just by adding the points that we want to that we consider to be 0 using this button here on the left. So for example, I think this is a 0, I think this is a 0, I think this is a 0, 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 probably this is a 0, and this is a 0, and goes down here. Probably there's nothing here to really fit, so I don't want to waste too much time. And I think all this area is actually a 0. It's just we're looking at some effects of the acquisition instrument that we used. And this is a 0, this is a 0, this is a 0, this is a 0. Now, please consider that putting everything here to 0 in this region is my idea based on my experience. I'm not actually sure if it's the best thing to do. For now, it's what I will be doing for this spectrum. And I also will put 0 in this region. This is because usually there's not much going on from after 1800 to about 2700, more or less. But here I don't see any real signal. I think that probably this is all caused by the machine is not a real Raman spectra in that area. So if I do like this and remove the baseline, what I have obtained is something like this that is not, it's far from perfect, but it gives us a little bit a better understanding of what we are doing. What we can do, let's Control Z to go back. I can even remove better the baseline in this region going like this. For example, if I know that this area should not have anything, or if I think that what's in this region is too weak to be considered, I can just remove it. I just need to remember that this is an approximation that I'm doing, and I'm not sure if what I'm doing is correct or not for now. Another thing we can do when working with a long spectra like this, because this goes from basically close to 0 centimeters minus 1 to more than 4,000 centimeters minus 1, this is a very long, very extended spectra. What we can do is to actually cut it and work with the cut pieces. This usually works much better and it's much easier to remove a baseline. So I strongly suggest you to never work with spectra that are this large, because of the baseline removal gets more and more complex as we increase the window, the size of the window. So let's clear up, and first let's cut our spectra. Let's go to data range, and here I will tell the software that I want only the data that goes from 500 centimeters minus 1 to probably 1750. Extract. As you can see, the baseline looks much more straight in this sub-region, so it should be easier to remove it properly. Please be careful when you do that, because we are losing the information of the other areas on the spectra. So save this file with a different name when you use a sub-region, otherwise you will lose information. And what we can do now is try to do the baseline automatically again and see if the software works better. Well, it's not bad. It's not my style for sure. Let's try with the polynomial auto. Bah, more or less the same result. Polynomial of the second degree. It should always, in ideally, it should always be something in the second degree if possible. It makes more sense, but it's not always easy, because there are many things that can affect the shape of the baseline. So it's a little bit complicated to say what is the real shape of the background. So let's do with my favorite again, which is background by lines. And as you can see, I'm deciding on some approximations of the curve. If I remove the baseline in a different way, I will obtain different results. Oh, I need to put a touch here, otherwise the points can be. If I don't put a touch here, I can put points basically everywhere. But if I say a touch, the points will be always on the curve. So something like this. Let's try subtract, and this is the spectra, and this is something we can actually work with. It's not so bad. Still some noisy things going on in the bottom here, but more often than not, we are not really using this information. Actually, we don't know if these are real bands or not. It's very difficult to know. Okay, so we have a workable sub spectra, workable spectral region that we can take care of. What we can do from now is, no, we don't need to work with the data range anymore. We did our baseline removal. What we can do from now is to have a look at the noise filtration options. So we can choose the degree of the smoothing, the size and the height of the smoothing. We can also despike, which usually removes small spikes, but in this case we don't have spikes, and if we run this, it actually damages the data. We have a lot of options here. As you can see, the smoothing takes the average over a few points, and if we increase the height, for example like this, doesn't affect much, but if we change the number of points that we use, we can totally destroy the data. We need to be careful when we do something like this. If the size is very small, it's a minor adjustment, but still it changes some relative intensities, as you can see. You need to be careful about that. And if we keep the height low and the size low, the adjustments are very minor. It gets a little bit stronger as we increase this height and size. So be careful, try to keep it low and increase it progressively in order to polish data that is not so clean. In this case, if we use a size 5 with a height 1, we don't do anything. There's nothing that we don't do any serious smoothing until we go to 7, and then it starts to smooth things down a little bit. Well, I will keep the data as it is. I will don't use the smoothing. I strongly suggest you not to use smoothing unless it's necessary, unless the data is very, very rough, noisy. Okay, here we have with our sub region of data, we open our spectra, and what we can do next is to start to do some proper fitting of this area. And how we do that, in order to do spectral fitting, we select this function here, and we start to add peaks at specific positions that we recognize are potentially peaks, Raman peaks in this case, like this. Here we can control, with this option we can control everything about our peaks, like what kind of function we are using, Gaussian or Lorentzian. The shape of the bell of the peak changes a little bit. I always use Gaussian Lorentzian, for example. But let me clear this 1 second and let's hit search. If we hit search, as you can see, it finds only the main results. We can search you can change the parameters of the search like this to try to make it fit more peaks. Here we could achieve 4. if we decrease the level to 1, for example, and the size to 5, this is the fitting he proposed to us. You see, it's not a very powerful instrument. Well, if you hit search, he actually does a better job now. It's not a very powerful instrument because it still fails at finding, for example, this, and in this area also makes a little bit of a mess. So be careful if you use the automatic search function. Try to use at the beginning level a low level and a low size to try to find even very small bands. If you go too small, as you can see, it fails. Oh, if I don't use 5, it doesn't actually find much. And this is with the quite clean spectra. If the spectra is more noisier and has more bands, more sub bands, the result is even worse. So be careful with search. I don't recommend using search unless it's absolutely necessary for you. What I recommend to try to do is to clear everything and go for a manual peak hunting like this. 1, 2, 3, 4, 5 here, 6 here. There's a shoulder here. I will not identify it as a peak for now. Here, 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 and here. We can approximate the curve. Looks like a mess, but then we fit and try to fit the parameters of each one of the band I added in order to be as close as possible to the spectra. The result is not excellent, and we can just fit a couple more times. So every time it gets a little better. Every time it gets a little better, but still, as you can see here, it fails completely at finding this one. Here is not excellent. Here also makes a little bit of mistake, and it doesn't. We didn't actually find these ones, and here also there is some problem. So what we can do now is to add some missing bands here, here, and here, and probably also here. No, 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 the last one is not a band. And here, and fit, and see if it will take a few trials to make it work well. As you can see here, it's on spot, and here is still trying to find this place. Its place. So we need to hit fit a couple of times, well, a couple dozen of times, in order for the software to do a good job. And here it improved a lot, but still we have an error here. You see, the fitting curve is down here, but the real curve is up there, so we will need to put another band there in order for this to be fitted a little bit better. Not always perfect. It's not always possible to obtain a perfect fitting, and we can actually do something to improve the chances to get a good fitting, and I will explain you how in a while. So this is not so good fitting. I will remove this peak here because it doesn't make any sense, and I will add back a peak here, and I will adjust this peak so that it goes here and it fits here. As you can see, we are now very close, so the software should do a better job at finding it. Yeah, as you can see, nice result here. Still here, the fitting doesn't go to 0 as fast as it's supposed to go. Here also, the real spectra is down here and the fitting is up here. It means our fitting is good, but it's not excellent. It's not very high quality. So let's do something else. This Spectre is not very complicated, as I said, but it has some sub-regions that are a little bit more difficult than others. So let's cut it again. We go from 1100 to 1350 in this case. We extract this data. So again, we are working with a sub-region. We go back to baseline and we make an hypothesis that this, and of course this are all 0 points. And now we have not we have to worry only about this relatively small region. We try to put our peaks back, one peak here, two peaks here, here, here. There's a shoulder here, so we will put a peak here, a peak here. It's impossible for this peak to cover this area, so there's probably a peak here in the middle, at least. And also the symmetry of this band is a little strange, so probably there's a peak here. Let's see how we are doing. If we use the approx function, it's a little bit too rough at the beginning. We got some things right, but let's adjust. It doesn't allow me to move it at this moment. Means it's still calculating. Well, let's clear it a little bit. Let's try to use search again and see what it does. As you can see, it misses a lot of information. Clear. Let's go. We are working a little at a time, trying to get the best result that we can from this data. Now, let's work. Oh yeah, it's working on the last peak. So we should pick one at a time. Okay. Let's do fit instead of approx. This process will at the beginning keep the white as we put it, and hitting fit a couple of times will go quite close to the result we expect. Yeah, in this case, I don't agree with these two, and these two overlapped, which is not what I intended to do, and it's not correct, I think. So we need to work a little bit more on the spectra, but as you can see, the result is not so bad. Please remember that there are infinite solution for a spectra. So you need to try to work with the minimum amount of bands that gives you the closest result possible. In this case, I will open peaks here. As you can see, we have all the peaks: position, intensity, width, the Gaussian coefficient. And what I want to do is to make this 1, 2, and 70, which is probably this one, go to 1, 2, and 90. Apply. So it moves here because I don't think it's the correct position. Let's close it 1 second. Let's it fit and see what happens. No, you can see, it's going up again. Okay, so I was not so wrong. As you can see, the result now here is pretty good. Here is pretty close. Here is still good, good, good. As you can see, here is like a triangular shape in the original data, and this is because the number of points of the original data is not so dense. It goes back here, not so bad, not so bad, not so bad. Again, I don't agree with these two. I think that the band at 180, from my experience, this is unlucky because it takes human experience to know what to do. In my experience, this is probably the strongest and the stronger, and this should be weaker by comparison. So let's see if Well, now it's pretty close, so I think we are done. This is an example on not perfect, but more than acceptable result. And what you can do is that you can copy this fitting that we just obtained. And when you open a new data that doesn't have any fitting yet, what you can do is paste your previous fitting. So if the samples have the same bands and at the more or less the same intensity, in this way it's you don't need to fit from zero. You can recycle the fitting you used previously for similar data. And when you save, you need to save as and use NGS so that you can will save the fitting along with the data. Okay, this is probably a correct way of fitting this. Well, correct. It's a personal opinion, but it's close enough. What happens if we use a different amount of bands? For example, if we do like this, which is closer to what it does with the automatic pick finder, you can see that there are some approximations that don't work very well. Like here, it misses one peak. It goes a little bit crazy in that area. Also here, the shape is strange. It doesn't go to zero. It tries to go to outside of this range. So you need to be careful. This is underfitting. We are using less bands than necessary. On the other hand, if I start to get crazy and say, oh no, I need to use as many bands as possible because they do a better approximation of the data, yeah, this is correct. The more bands you use, the, the more you can approximate. But using too many bands creates a lot of fake data for a lot of fake bands and doesn't have any physical meaning. And this is a overfitting. So you need to be careful to use the minimum amount of bands that produce a good fitting. And in order to do so, the best way to start with just a few bands and progressively add more and more bands. So let's clear it again. For example, I can start as I showed you before with something like this, and I hit the fit button a little bit of times. When I see that the fitting starts to approximate the data, I can try to add the missing information, the missing bands in the specific points, and hit fit again so that they will reach the ideal position. I still think these two bands are only one, so I can remove the one at 1 to 50, for example. Like, well, as usual, this doesn't work very well. Uh, so so difficult. Okay, like this, and fit again, and you will see that the fitting goes well. So I was over fitting in in this area, and now the fitting looks better. And we can still improve a little bit, but it's not so far from truth. And this is a little strange because these are too close by intensity and position, so I will need to change the relative intensity. But we can talk about and discuss about this result in the next video. For today, this is more than enough. Thank you for listening.